So today we're going to look at a really cool infinite product that I just learned about. And so it's motivated by another pretty famous product that you often learn about in calculus called the Wallis product. And it involves pi. And in fact, what we have is pi over 2 is equal to 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5 times 6 over 7 times 8 over 7, and so on and so forth. So I think you can see the pattern repeating here. And so the question that we'll answer here today is there something like this for E? And in fact there is, and here's the expression we're looking for. So notice we have E over 2 is this product. Notice that all of the terms are the same, except we raise the 2 over 1 to the half power. The next two terms are raised to the quarter power. The next four terms to the 8th power, and so on and so forth. And I found this in the 1980 issue of the American Mathematical Monthly, and the title of the article is An Infinite Product for E by N. Pippinger. Okay, so let's maybe get to this. We're gonna prove this statement right here. So I'm gonna maybe introduce some notation. So let's set P equal to, well, our product. So I'm going to take this 2 over 1 to the half and just write it as the square root of 2 out front. And then after that, we'll have the product as n goes from 2 up to infinity of, well, we've got to see some sort of pattern for all of these terms. And here's the pattern that we'll need. So let's see, our numerator will look like this. We'll start with 2 to the power n minus 1. And after that, we'll have 2 to the n minus 1 plus 2. That'll be squared. And then 2 to the n minus 1 plus 4. That'll be squared. Ending way up here at, let's see, it'll be 2 to the n. And maybe I'll write right before that, we have 2 to the n minus 1, and that'll be squared, times 2 to the n. Okay, so maybe the best way to see that this is the right pattern is to look at this term right here. Maybe here there's nothing in the middle, but this 4 times 6 times 6 times 8 shows us what's going on here. So this 2 to the n minus 1, that's like 4 in this case. This 2 to the n, that's like 8 in this case. And then this 6 would be like this term right here. Oh, and I just realized this should be minus 2. Because I've got just a product of even terms right there. Okay, and then what do we have in the denominator? Well, the denominator is going to be pretty similar, but now everything is paired off. We have 3 times 3, 5 times 5, 7 times 7, and so on and so forth. So in fact, it's going to look like this. 2n minus 1 plus 1 squared times 2n minus 1 plus 3 squared, and that's going to go all the way up to 2 to the n minus 1 squared. And we can see that kind of happening in this term right here. So the 2 to the n minus 1 plus 1 is like 5. The 2 to the n minus 1 plus 3 is like 7. Okay, and then just so that we don't forget, we need to raise this whole thing to the 1 over, let's see, it'll be 2 to the n power. This is 1 over 4, 1 over 8, so on and so forth. But now I'm going to introduce some notation just so that we can work with these terms individually. And that notation will be, well, I'll still have this square root of 2, and now I'll have my product as n goes from 2 up to infinity. And now I'm going to write this as a sub n over b sub n, all raised to the 1 over 2 to the n. Okay, so that means our a sub n term is like this whole thing which is in the numerator, and our b sub n term is that whole thing that's in the denominator. And now we're going to work on these a sub n and these b sub n terms. And we'll do that by starting with the a sub n term. Okay, so let's take our a sub n term, which, like I said, is this thing that's in the numerator. And before we even get going, I'm going to multiply by 2 to the n over 2 to the n. That'll square this 2 to the n, and then I'll have 2 to the n minus 1 over 2 to the n, which will give us 1/2. And that'll be nice because now everything will be squared. So that'll give us 1/2, and then we'll have 2 to the n minus 1 plus 2 quantity squared. And then after that, 2 to the n minus 1 plus 4 all squared, all the way up, 2 to the n minus 2 squared, and then 2 to the n squared. Okay, so that's what we've got going on here. And then what I'll do from there is take all of these squareds, and since everything's squared, I can factor that square out of the whole thing. And next up, I'll notice that each of these terms are even, which means I can factor a 2 out of them. So this is going to give us 2, and then we'll have 2 to the n minus 2 plus 1. So that's that term. And then let's see, we can factor a 2 out here, and we'll have 2 to the n minus 2 plus 2. And then way down here, we can factor a 2 out, and we'll have 2 to the n minus 1 minus 1. And then finally, factoring a 2 out of this will give us 2 to the n minus 1. And then I guess pretty importantly is how many terms do we have here? So let's count up the number of terms we have there, because notice that we have a 2 attached to every one of those terms. And since we have a 2 attached to every one of those terms, we'll have 2 to whatever that power is. And you can pretty easily calculate that there are 2 to the 2 to the n minus 2 total terms. Great, and you can maybe see that because we're starting at 2 to the n minus 2 plus 1, and we're ending at 2 to the n minus 1. So what do? You take the difference of those and you add 1, and that gives you, well, the number of terms. So let's use that to factor this 2 to the 2 to the n minus 2 out of the whole thing. Oh, but we need to square it. But squaring it will raise this exponent in the exponent to a n minus 1. Okay, so let's see. That's going to give us 2 to the 2 to the n minus 1 over 2. And then what do we have from there? Well, notice, let's maybe be careful about this. We have this term right here, this 2 to the n minus 1 plus 1, 2 to the n minus 2 plus 1, 2 to the n minus 2 plus 2. The next one will be 2 to the n minus 2 plus 3, ending at 2 to the n minus 1. Well, notice that's like almost a factorial. It's not a factorial because it doesn't descend all the way down to 1, but it at least descends part way. But we can make up for that by noticing that if we write 2 to the n minus 1 factorial over 2 to the n minus 2 factorial, that'll make everything happen. So let's just review what we did. So this 2 to the n minus 1 factorial will be a falling product starting at 2 to the n minus 1. So there we've got 2 to the n minus 1, that minus 1, so on and so forth, all the way down. But notice we need to cut it off at 2 to the n minus 2. So that's not present. So we can do that by dividing by 2 to the n minus 2 factorial. Okay, so that's our a sub n term. So let's maybe get that up and then we'll work on our b sub n term. Okay, so we just found a simpler version of our a sub n terms, and now we're going to do the same thing for our b sub n terms. Okay, so let's do that. So let's notice that b sub n can be written as 2 to the n minus 1 plus 1 times 2 to the n minus 1 plus 3 all the way up to 2 to the n minus 1, and then that's all squared. So I just took the square out of that. And then next up what I'm going to do is multiply by a version of 1 that fills in the gaps here. So notice that we're missing something between 2 to the n minus 1 plus 1 and 2 to the n minus 1 plus 3. And that would be 2 to the n minus 1 plus 2. And then likewise, in the middle here, we'll put a 2 to the n minus 1 plus 4. And then at the very end, we'll put a 2 to the n. But now if we multiply those in the numerator, then that means we also have to multiply them in the denominator. But I'm going to use a slightly different form in the denominator, and I can totally do that because this looks exactly like what we had in our a sub n term. So we should be a little bit familiar with what that looks like. So in the denominator, I'll write it in the form 2 to the 2 to the n minus 1. And then we'll have our, let's see, 2 to the n minus 2 plus 1 multiplied all the way up to 2 to the n minus 1. and then that's all squared. Okay, cool. But now let's see. In the numerator, we've got this descending product from 2 to the n down to, well, right before 2 to the n minus 1. And then in the denominator, we've got this descending product from 2 to the n minus 1 all the way down to right before 2 to the n minus 2. So we can similarly complete those into a factorial like we did in this a sub n term. And let's see what we get if we do that. So we'll have 1 over 2 to the 2 to the n minus 1. So that'll be from this denominator term right here. And then after that, we'll have our 2 to the n factorial squared. That'll be from the completion of that descending product. And then we'll also have a 2 to the n minus 2 factorial squared. That'll be as like a correction for the completion of the product that's happening in the denominator. But then the completion of the product that's happening in the denominator, together with the correction of what we have in the numerator, will leave us with 2 to the n minus 1 factorial, all raised to the 4th power. So we've got something like that for our b sub n term. So now that we've got that, well, let's get those both on the board, and then we'll calculate their quotient in maybe simpler terms. We just did a decent amount of work to write the numerator and the denominator of the terms in our product in like what I'll call, maybe it's not a simpler way, but it's a way that at least the numerator and the denominator will interact with each other nicely. And that's what we got. And now let's look at their quotient. So we have a to the n over b to the n. That's of course part of our product there. And what will we get? Well, this b to the n has a 2 to the 2 to the n minus 1 in the denominator. That'll flip up to the numerator, giving us a 2 to the 2 to the n. That's because when we add 2 to the n minus 1 with itself, we get 2 to the n. Great. And then we've got that's over 2. That comes from this term right here. Then next up, this 2 to the n minus 1 factorial to the 4th will flip up and combine with, well, itself squared in the a sub n term. That'll give us 2 to the n minus 1 factorial to the 6th power. And then in the denominator, we've got some interesting stuff as well. We have a 2 to the n minus 2 factorial to the 4th power. So that's from this term and this term. And then finally a 2 to the n factorial squared. So we have something that looks like that. Now, how can we rewrite our product? Well, it'll be the square root of 2. And then we have our product as n goes from 2 to infinity of this quotient raised to the 1 over 2n power. So let's see. Raising 2 to the 2 to the n to the 1 over 2n power will simply give us 2 because it's taking the appropriate root. So here we'll have 2 here. Then in the denominator, we'll have 2 to the 1 over 2n. Okay. And then let's see. We'll have 6 over 2 to the n, but that's going to give us what? Well, we'll have 2 to the n minus 1, and then 3 over 2 to the n minus 1, after like canceling out the stuff that we are able to cancel out. Okay, and then where do we go from there? Well, we're going to simplify the denominator similarly. So let's see. Here we'll have 2 to the n minus 2 factorial, and then this will be 1 over 2 to the n minus 2, just based off of having a 4 in the numerator and a 2 to the n in the denominator. And then likewise, we'll have 2 to the n factorial, and then 1 over 2 to the n minus 1. So there's where we're at the moment. Now, I'm going to bring that up to the top and write it as a limit of a partial product because we'll need it like that in order to do our final, maybe, simplification. So this is essentially where we left off. I just changed that infinite product to a limit of a partial product. And the really nice thing about doing that is that I can change this single product into a combination of a bunch of products because, like I said, this is a finite product at the moment. We're just taking the limit of that finite product. So that's exactly what we'll do. So we'll have the square root of 2. I might as well take that out front. And then the limit as n goes to infinity of, well, let's maybe do the product as n goes from 2 to capital N of 2. that simply gives us 2 to the n minus 1, because we're multiplying 2 to itself n minus 1 times. So that's that term. And then in the denominator, we'll have, well, I'll write this as the product as n goes from 2 up to n of 2 to the 1 over 2 to the n. Great. And then I'll do a similar maybe distribution across the other terms. Okay, so we'll have a product as n goes from 2 up to n of, now this is 2 to the n minus 1 factorial raised to the 3 over 2 to the n minus 1. And then in the denominator, I have my product as n goes from 2 up to capital N. We have 2 to the n minus 2 factorial, 1 over 2 to the n minus 2, and then finally my last. So again, it's a pretty similar product, but now it's 2 to the n factorial, all raised to the 1 over 2 to the n minus 1. Okay, so that's where we're at the moment. And then from here, what I'll do is do a re-indexing of each of these products. And I'll re-index all of them into this 2 to the n power. So I'm going to make them look like 2 to the n factorial. So that means for this product, I need to take n and replace it with n plus 1, because that'll take n minus 1 and turn it into n. And then for this product, I need to take n and replace it with n plus 2 for, fairly similar reasons. Okay, so now let's see what we have. We have the square root of 2. We have our limit as n goes to infinity. We have all of these terms, so those just like kind of come down for free, if you will. So 2 to the 1 over 2 to the n. So there we have that. And now here's where it all kind of happens. So now when n plus 1 is equal to 2, n is equal to 1. So that's going to give me the product from 1 up to n minus 1 of, now it'll be 2 to the n factorial, and we'll have 3 over 2 to the n. Okay, so there's that term. And then in the denominator, I'll have, well, this will be the product from, well, when n plus 2 is equal to 2, n is equal to 0 up to n minus 2. And then we'll have 2 to the n factorial, and that'll be raised to 1 over 2 to the n. And then finally, one more term, which I don't need to re-index. So that's the product as n goes from, let's see, 2 up to capital N of 2 to the n factorial. But instead of writing that as 1 over 2 to the n minus 1, I'm going to write that as 2 over 2 to the n. Because now notice that this numerator term will cancel those two denominator terms. But that's only for the terms that they have in common, which isn't everything. Notice this starts at n equals 1, this starts at n equals 0, this starts at n equals 2, and then they end at different spots as well. So let's see what survives. So we need to take the most restrictive parts of each product. So each of them have an n equals 2 term, and each of them have all the way up to an n minus 2 term. So that means all of those will cancel. So what does that mean survives here? Well, that means that the n equals 1 term will survive and the n equals n minus 1 term will survive. So that means we need, well, n equals 1 term, which is, let's see, it'll be 2 factorial raised to the power 3 over 2. So we can think of like just pulling that out and then changing this product so it starts at 2 now. And then let's also pull out the n minus 1 term. So that'll be 2 to the power capital N minus 1 factorial, and then 3 over 2 to the capital N minus 1. Okay, and then maybe we'll change this so now it stops at n minus 2. Okay, so let's maybe rewrite this a little bit differently. So now we have this product times these two terms that we took out. And then likewise, we need to take 2 terms out of this product as well. The n equals 0 term and the n equals 1 term. So let's do that. We'll make this start at n equals 2, And then, well, the n equals 0 term, well, that'll be 2 to the 0. That's simply 1, so we don't need to worry about that. And then the n equals 1 term, well, that'll be 2 to the 1 factorial to the power 1 over 2. Well, that's simply 2 to the 1/2. So that's the n equals 1 term. Okay, so we pulled that out. And then what do we need to do over here? Here we need to pull out the n and the n minus 1 term. So that'll make this thing end at n minus 2. So let's see. The nth term is 2 to the power n factorial, and then 2 over 2 to the n factorial, and then we'll have 2 to the n minus 1 factorial, and then 2 over 2 to the n minus 1 factorial. Okay, so that's what we get from pulling those terms out. But now we can push these together, and we'll have 2 to the n factorial to the 1 over 2 to the n plus 2 over 2 to the n, which gives us 3 to the 2 over n. And so that'll make all of these terms cancel. And then while we're at it, we might as well cancel this 2 to the half term with this square root of 2 term that was kind of like hanging on for a while. Okay, and now that we have all of that simplification, let's start with something clean and do the final part. Okay, so this is where we left off. I did do a tiny bit of simplification, but hardly any at all. So now let's start with maybe the final steps. And let's start by looking at this boxed yellow term. So I can use maybe exponent rules to rewrite that as 2 to the 1/4 plus 1/8 plus ending at, let's see, we'll have 1 over 2 to the capital N. But now I'm going to do something that's a little bit of a cheat, but it actually works in this case given that all the limits exist, and I'm going to take the limit of this as n goes to infinity. But look, this is a geometric series where the starting term is 1/4 and the common ratio is 1/2. So this actually tends to 1/2 as n tends towards infinity. So that means I can take everything inside of this yellow box and replace it with 2 to the half power. And that's exactly what we'll do. But that's actually going to allow us to cancel this 2 to the 3/2 power down to just 2. So let's cancel that out, and then that just becomes 2 in the numerator. And now let's see what else we have. So this 2 to the n minus 1 factorial to the power 3 over 2 to the n minus 1 will simplify with this term right here. So notice you can take the difference of their exponents, and that'll have the effect of just making this one disappear and changing this exponent to a 1. But now the exponent of these two is exactly the same, which allows for a little bit more simplification. Okay, so let's see what we have. So this is going to be equal to 2. I'll take this 2 out. And then the limit as capital N approaches infinity of 2 to the n minus 1. And now we have 2 to the n minus 1 factorial over 2 to the n factorial raised to the power 1 over 2 to the n minus 1. And now, even though I haven't used the whole board, I am going to start with a new one so we can finish it off all at once. So here's where we left off. And now we're going to finish it off with something called Stirling's approximation, which I just recorded a video for. It's probably on the channel already. And that says that m factorial grows asymptotically to the square root of 2 pi m times m over e to the m power. So that means that whenever you're working with factorials in limits, you might as well just use the Stirling approximation, because that means that, well, essentially their quotient has the limit of 1, so just a 1-to-1 replacement will not change the value of the limit. Okay, so let's do that. So now we'll have 2, and then the limit as n goes to infinity, we have this 2 to the n minus 1 term. And then let's see, we can replace this with the square root of 2 pi times 2 to the n minus 1. So that'll give us 2 to the n times pi. And then let's see, we'll have 2 to the we'll have 2 to the n minus 1 over e, and then all of that is raised to the 2 to the n minus 1. So that's just using Stirling's formula where m is 2 to the n minus 1. And now we're going to use Stirling's formula again where m is 2 to the n. So that'll give us the square root of 2 to the n plus 1 times pi, and then 2 to the n over e raised to the 2 to the n. And then that whole thing is raised to the 1 over 2 to the n minus 1. Now we're ready to like almost finish it off. So here we'll have 2, our limit as n goes to infinity. 2 to the n minus 1 is still just hanging on. And then let's see, these two should cancel pretty easily, and they do. They'll cancel down to a square root of 2 in the denominator raised to this power. But maybe we could write that as a 1 over the square root of 2 raised all to the power 1 over 2 to the n minus 1. Okay, so that's what we have from that. And then the exponent here is the reciprocal of the exponent there, so those just straight up simplify. So those will simplify to, let's see, 2 to the n minus 1 over e. And then the exponent here is twice the exponent here. So that'll simplify to, well, a 2 for the exponent. But since that's in the denominator, we can take the reciprocal. So that'll give us e squared over 2 to the 2n, because again, our new exponent is 2. Okay, so now let's see what simplifies. Notice we've got 2 to the n minus 1, 2 to the n minus 1, and 2 to the n. So this, and this will cancel out to a 4 in the denominator. But canceling out to a 4 in the denominator will cancel this 2 down to a half. And then, well, we're just left with e squared over e. So those will cancel also just to an e in the numerator. So we have e over 2. But now look, as n goes to infinity, this exponent is approaching 0. And so we've got a number to the 0 power, which is equal to 1. So the remaining limit is simply 1, meaning at the end we have e over 2, which was our final goal. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.